Okay, now our idea is now to replace this quantizer with the model that we talked about previously. So now I'm abstracting again. I'm going through the C to D converter. I'm sampling here at a very high rate. I'm going to quantize, go through this filter, and then I'm going to decimate. And so if you allow me to replace the quantizer with this additive noise source, then I end up with a picture like this. Notice here the sampling period I'm picking is 1/nth of the cutoff frequency of this analog signal. So I'm assuming that this is band limited to omega sub n, and I'm oversampling by a factor of m. I now have this discrete time signal. I'm adding the quantization noise, where the quantization noise is modeled as wide sense stationary, uniformly distributed between plus or minus delta over 2. And if you just figure out what the variance of that is, the variance of that is going to be 1/12 times delta squared. So that's what the variance of this noise is. And what all these assumptions basically have allowed us to do is take a very highly nonlinear problem. Quantization is a very highly nonlinear process, and represent it or replace it by a problem that we know how to analyze. And fortunately, it turns out that carrying out the analysis with this model is actually pretty reasonable to within the accuracy that you would be thinking about. And what also lets you get away with it is in talking these things through, you're thinking in terms of how many bits it takes to represent a signal, and one additional bit, if this variance is, so delta, I can't write with that. So delta is equal to 2 to the minus b, and so you're allowing a lot of spread in this variance when you're talking about changing from by, for example, 1 bit. And that's kind of what lets you partly get away with this analysis. Okay, so here's the system. Now, I kind of want to draw your attention to this equation. What this equation says is that the autocorrelation function of the output is the autocorrelation function of the input decimated. So what it says about the power spectral density at the output of the decimator. Now, what you kind of remember when we talked about the decimator, so I put a signal through a decimator, then the Fourier transform of the output is related to the Fourier transform of the input. There's a 1/m factor, and then, of course, the replication of the Fourier transform. We can't talk about the Fourier transform of x of n, because x of n is a random process. It goes from minus infinity to plus infinity. It has infinite energy in it. We can talk about its power spectral density, and what this is telling you is that, in fact, the power spectral density of the output is going to be 1/M times the power spectral density of the input replicated. And we're assuming that we've done enough filtering at this point so that there won't be aliasing in the power spectral density. So we're grossly oversampling. And by the way, one of the things this kind of also you want to have clear in your head is that since a random process does not have a Fourier transform in the usual sense, how do you talk about its bandwidth? Well, you talk about its bandwidth in terms of the width of the power spectral density, and then sampling issues in terms of how fast do you have to sample, what's the bandwidth of x of n, has to do with what the bandwidth of the autocorrelation function is. And those are all things that are talked about in some detail in 6011 and in the 6011 notes. Okay, so we go through this process, and I'm assuming that the input signal is a random process, so it's described by its power spectral density. So its power spectral density is this triangle. And then the power spectral density of the quantization noise is constant, and it's constant because we're assuming that the quantization noise or quantization error is white. And also it has a level which is the variance of the quantization noise. So it has a level which is equal to this. And just remind yourself that the reason that its level, the amplitude of that power spectral density, is the variance, the reason for that is an equation that I have right here. Because that equation says the variance, which is the autocorrelation function at zero lag, is the area under the power spectral density. If that power spectral density is a constant, when I take 1 over 2 pi times the integral, I'm going to end up with whatever that amplitude is. And I draw your attention to it because you'll be kind of seeing that in some other slides. So the level of the power spectral density is also the variance for a white process, not for, in general, a colored process. Okay, so now let's see. We go through, we've talked about what the power spectral density looks like here. We have the power spectral density of the signal, the power spectral density of the noise. We now go through a low-pass filter, which has a cutoff frequency of pi over m, and then we're going to decimate. And so if you look at this picture, let's see, for the top picture, when you go through the low-pass filter, does it change anything about the power spectral density of the signal? Well, it doesn't change the shape. It just scales the amplitude by 1 over m, and that's because of what happens to this equation in the frequency domain. Does it change anything about the quantization noise? Well, yes, I've gone through the low-pass filter. The low-pass filter has the cutoff frequency here. So now I'm going to throw away this part of it. And now when I take that picture, the output of the low-pass filter, and I go through the decimation, I'm going to divide by m. That'll get rid of this m. And I'm going to, well, why do I divide by m? This doesn't tell me to divide the power spectral density by m, because what's going to happen in general in this equation is I'm going to alias. And if you just kind of think it through, before the low-pass filter, if I decimated, you haven't gained anything. So there won't be a 1 over m. So where does this 1 over m come from? Well, if you look at taking this and low-pass filtering, then you get rid of some of the noise.